At 01:20 in the morning on November the 5th, 1943, the last radio traffic attributed to the aircraft included the request, "Turn on radio range." A clock later recovered from the wreck was found stopped at approximately 01:21. That single minute marks the boundary between an operational heavy bomber and a recovery site later investigated by U.S. accounting teams. This is the recovery investigation of consolidated B-24D, serial number 4240972. The objective is not to salvage a machine, but to close the file on 9 airmen listed as missing in action from the Second World War. The primary constraint is not the passage of time, but the location of the evidence. The wreckage lies high in the mountains of Morobe Province, Papua New Guinea, at an elevation of approximately 10,800 feet, on steep, unstable terrain. The aircraft belonged to the 63rd Bombardment Squadron, 43rd Bombardment Group, 5th Air Force. It departed Dobodura, New Guinea, for an armed reconnaissance mission over the Bismarck Sea. Later in the mission, the crew radioed that they had made 3 direct hits on the convoy and destroyed the target. The return leg required navigating through a heavy frontal system without visual references. No further radio contact was received after the last transmission. The silence that followed lasted for nearly 6 decades. For decades, U.S. accounting authorities carried the aircraft and its crew as missing and unaccounted for. Contemporary records did not produce confirmed survivor reports. The wreckage remained undiscovered because the terrain and access constraints actively concealed it. The impact point was high in steep mountain country where rock movement and weathering can bury and re-expose debris over time. In March 2002, a local government official, acting on information tied to the mountain site, contacted U.S. personnel through the U.S. Embassy and turned over aircraft data plates, human remains, and 3 identification tags. That handover triggered a formal recovery investigation and subsequent excavation by U.S. accounting teams. The gap between the loss and the discovery defines the engineering challenge. We are not looking for a crash site where debris is scattered on a flat jungle floor. We are looking for a debris field that has been churned by decades of geological movement. The site is a mixture of aluminum rock and ice. The aircraft did not just impact the terrain, it became part of the mountain. The clock found stopped at approximately 01:21 provides a compelling narrative anchor. It is consistent with the timeline implied by the last radio traffic, but it does not by itself prove a precise second-by-second sequence. This reduces the likelihood of a long, survivable emergency sequence, but the official record still lists the cause of the crash as unknown. The evidence is consistent with a high-speed impact under power. It sets expectations for what the site can still preserve. The recovery mission faces a dual challenge. First, the team must verify the identity of the aircraft using serial numbers found on the data plates. Second, they must locate biological evidence of the 9 crew members in a shifting field of loose rock. Over decades, exposure, gravity, and rock movement can shift components downslope and separate heavy and light materials across a broad debris field. To achieve the objective of full accounting, the investigation must reconstruct the geometry of the crash. We must understand how the aircraft hit the wall and where the momentum carried the crew. If we misinterpret the angle of impact, we will look in the wrong soil for the remains. The evidence suggests the aircraft is no longer where it hit. It has slid and been buried by the mountain itself. In 2003, teams worked a steep, scattered debris field under severe safety constraints to recover small personal effects and human remains. The investigation begins with a precise correlation of the historical record and the physical reality. The radio log gives us the time. The site gives us the physics. The hunter gave us the location. Now the recovery team must insert a forensic process into a hostile alpine environment. The question is not just where the plane is, but how much of the crew remains recoverable after 60 years of exposure to the elements. 10,800 feet. This elevation defined the access problem that shaped the recovery effort decades later. The official record states that the aircraft crashed for unknown reasons in Morobe Province after the mission. However, the sequence, night weather, loss of reliable positional awareness, and a high mountain impact, fits the broad pattern of controlled flight into terrain. Where a functioning aircraft meets terrain the crew does not see in time. The machine is functioning correctly, the crew is performing their duties. But the situational awareness has decoupled from the physical reality of the ground. To understand why a highly trained crew flew into a ridgeline, we must analyze the navigation technology of 1943. One navigation aid used in that era was the low-frequency radio range system. This system guided aircraft by transmitting directional radio beams defined by audible Morse code signals. If the pilot was to the left of the course, he heard the letter A, which is a dot followed by a dash. If he was to the right, he heard the letter N, which is a dash followed by a dot. When the aircraft was perfectly aligned with the station, the two signals merged into a steady, solid tone. This was an auditory highway in the sky. The last reported transmission included a request to activate the radio range. The wording suggests the crew was trying to regain a dependable navigation reference, but the precise cockpit context cannot be reconstructed from the message alone. In tropical weather systems, static and interference can drown out weak navigation signals and make radio guidance ambiguous. Without that solid tone, the pilot is blind in the clouds. He was likely searching for the beam when the aircraft intersected the terrain. The impact physics at cruising speed against a solid rock face dictates the condition of the wreckage. The aircraft did not slide to a halt. It shattered. The kinetic energy of a heavy bomber at cruising speed was converted instantly into deformation and fragmentation. The structure fragmented into thousands of pieces. Heavy components like the four Pratt and Whitney engines carried more momentum and punched into the scree, while lighter aluminum skin sections were thrown backward or scattered by the blast. The environment then took over the custody of the evidence. The crash site is located on a scree slope. This is a geological feature consisting of loose, broken rock that accumulates at the base of a cliff. A scree slope is not static ground. It is a slow-moving river of stone. Over 60 years, the freeze and thaw cycles of the high alpine altitude caused the rocks to shift and slide downhill. This movement acts as a natural burial mechanism. When the aircraft hit the rock slide, covered the debris. Season after season of avalanches added more layers of stone over the aluminum. This helps explain why search efforts at the time did not locate the wreckage. Pale rock and weathered metal can blend at distance, making a scattered field difficult to distinguish from natural scarring. From the air, the site looks like natural geological scarring. It was only when the slope shifted enough to expose a landing gear strut or a wing spar that the site became visible to a distinct observer on the ground. The wreckage is spread across a vertical distance of 200 yards. This dispersion is not random. It is sorted by gravity and mass. Heavier items sink deeper into the shifting rock. Lighter items stay near the surface or are blown downhill by the wind. The recovery team must treat the mountain as a dynamic container. The evidence is not sitting on the surface. It is suspended inside the rock pile. This environment changes the rules of engagement. We are not dealing with a jungle recovery where vegetation is the primary obstacle. We are dealing with an excavation that requires moving tons of rock to find ounces of biological material. The slope angle means that any disturbance can trigger a slide, burying the evidence further or endangering the team. The mountain hid the aircraft for 2 generations. Unlocking it requires understanding that the terrain is the active opponent in this investigation. The recovery operation is governed by a rigid atmospheric constraint known as the weather window. At this altitude, the air density is significantly lower than at sea level. This reduction in air pressure limits the lift capacity of transport helicopters. A helicopter that can carry a full load of equipment at sea level may struggle to hover with a partial load on the mountain. Furthermore, the mountain range creates its own microclimate. Warm, moist air rising from the jungle floor meets the cold alpine air, triggering sudden cloud formation. Visibility can drop from 20 miles to 0 in less than 15 minutes. The elevation and weather constraints shaped the operational tempo for the recovery element during the 2003 excavation. The team does not have the luxury of a leisurely survey. Every hour on the site is borrowed time before the clouds close in or the wind exceeds safety limits for extraction. Therefore, the first priority upon landing is not excavation, but positive identification. The team must prove that Site P0088 is indeed the resting place of B-24D serial number 4240972. Identification in aviation archaeology requires a process called material evidence correlation. It is not enough to find a liberator. Hundreds of B-24s were lost in the Pacific theater. To claim the site legally, the team must find a unique identifier that matches the historical manifest. This is rarely the large painted tail number, as paint degrades or peels away on exposed aluminum. The proof is found in the permanent steel data plates attached to major components. Finding a machine gun with a serial number that matches the log for the 43rd Bomb Group aircraft provides a definitive link. It converts a generic wreck into a specific legal entity. The survey reveals a distinct anomaly that aids this process. The site has been protected by what can be described as an avalanche seal. In Papua New Guinea, accessible wrecks at lower altitudes are often scavenged for scrap metal by local populations over the decades. Valuable copper wiring, aluminum, and steel are stripped away, leaving only a skeleton. However, burial under rock and the difficulty of access can reduce disturbance and slow some forms of deterioration compared with exposed lowland sites. When the team removes the top layer of scree, they find components that appear remarkably preserved. The aluminum skin retains its structural integrity. The data plates are legible. This preservation confirms that the site has high integrity. It has not been contaminated by modern interference or looting. The physical evidence found on the slope correlates 100% with the loss report generated after the radio range failure. With the identity locked, the mission focus shifts from survey to recovery. We know this is the correct aircraft. We know the crew was on board at the moment of impact. But the structural preservation of the metal does not guarantee the preservation of the crew. The violence of the impact and the shifting nature of the rock slope mean the human evidence will not be found in the cockpit seats. It will be fragmented and dispersed within the debris field. The team must now design a strategy to disassemble the mountain without destroying the fragile evidence it holds. The primary physical adversary in this phase of the recovery is the angle of the terrain. The crash site sits on a gradient of 45 degrees. This geometry creates a constant hazard. If a recovery team member dislodges a rock, it can trigger a slide that buries a lower section of the grid or injures a colleague. The laws of gravity do not negotiate with the requirements of archaeology. Therefore, the anthropologists and support staff cannot simply walk on the site. They must operate like mountaineers. This introduces a specific operational quirk unique to high-altitude recovery. The scientists must secure themselves with climbing harnesses and safety lines anchored to the rock face. They work tethered to the mountain while performing delicate excavation tasks. This is the integration of alpine climbing techniques with forensic science. The safety ropes allow the team to maintain a fixed position without relying on their footing, which minimizes the disturbance of the loose scree. To preserve spatial context on steep ground, the excavation approach prioritized controlled removal, careful mapping, and documentation before collection. In a standard dig, one might remove layers of soil evenly. However, on a shifting slope, removing the supporting matrix causes the evidence to tumble out of position. Instead, the excavators remove the soil around an artifact, leaving the object resting on a column or pedestal of undisturbed dirt. This method isolates the evidence in three-dimensional space. It allows the team to photograph, map, and record the precise orientation of a boot, a uniform fragment, or a piece of structure before it is physically touched. Only after the data is locked into the site grid is the pedestal cut and the object bagged. This preserves the relationship between the objects, which is critical for understanding how the aircraft broke apart and where the crew was thrown during the impact. Once the artifacts are mapped, the soil itself becomes the focus. Every bucket of dirt and rock removed from the grid must be screened. The team establishes screening stations where excavated material is passed through fine mesh to recover small personal effects and fragmented remains. The goal is to catch objects that are too small to be seen by the naked eye during the initial dig. This includes fasteners, data plates, personal effects, and most importantly, fragmented human remains. At this altitude, the physical cost of this labor is amplified. The thin air reduces the efficiency of the human engine. Carrying 5-gallon buckets of scree across a 45-degree slope requires disciplined energy management. The team forms bucket lines to move material efficiently to the screens. The screening process is manual and repetitive. It relies on the visual discipline of the operator to spot a tooth or a bone fragment amidst thousands of gray limestone chips. The recovery generates a massive volume of material. During the 2003 excavation, the team recovered additional remains and personal effects from a large volume of disturbed material, then transferred the evidence into controlled custody for laboratory work. The debris field was systematically dismantled. The result is not a collection of intact bodies, but a collection of biological evidence protected by chain of custody logs. The physical recovery is a process of controlled destruction. The site is taken apart piece by piece to extract the data it holds. By the end of the operation, the mountain slope has been returned to its natural state, but the history it held has been transferred into evidence bags. The challenge now shifts from the physical difficulty of the slope to the scientific difficulty of the laboratory. The team has recovered the pieces. Now they must prove who those pieces belong to. The arrival of the evidence at the laboratory in Hawaii marks a fundamental shift in the investigation. On the mountain, the challenge was physical access and geological stability. In the laboratory, the challenge becomes biological resolution. The recovery team delivered hundreds of bags containing osseous material. But these fragments do not automatically equal 9 distinct individuals. The discrepancy between the volume of recovered material and the legal requirement for individual identification creates the central technical hurdle of the outcome phase. The crash of a heavy bomber at high speed into a rock face results in severe fragmentation of the crew. Standard identification methods such as dental comparison rely on finding intact jaw structures. While the screening process on the slope recovered dental evidence, it is often insufficient to account for every crew member on a manifest of 9. When physical morphology fails, the investigation must pivot to the molecular level. The primary tool for bridging this gap is mitochondrial DNA analysis. Unlike nuclear DNA, which is found in the nucleus of the cell and degrades rapidly under environmental stress, mitochondrial DNA is found in the mitochondria, which act as the power plants of the cell. A single cell contains only one nucleus, but can contain thousands of mitochondria. This high copy number means that even in bone samples that have been exposed to freezing and thawing for 60 years, there is a higher probability of finding viable genetic material. This specific type of DNA follows a maternal line of inheritance. It is passed unchanged from mother to child. To identify the airmen, the laboratory must locate surviving maternal relatives for each of the 9 crew members. A sample is taken from a sister, a niece, or a cousin on the mother's side. The genetic sequence from the reference sample is then compared to the sequence extracted from the bone fragment. When the sequences align, the fragment is no longer an anonymous piece of calcium. It becomes a named individual. The environmental conditions that made the recovery so difficult provided a paradoxical benefit to the laboratory. Burial and high elevation conditions may have helped protect some biological evidence from heat and exposure compared with lowland tropical sites, improving the odds that mitochondrial DNA could still be recovered decades later. The process is methodical and time-consuming. It involves cleaning the samples to remove soil contaminants, grinding the bone into powder, and chemically extracting the genetic markers. This data is then cross-referenced with the material evidence correlation established during the site survey. The serial number on a machine gun proves the plane is the liberator. The DNA proves the bone is the pilot. By 2006, modern forensic analysis, supported by mitochondrial DNA and dental evidence, allowed U.S. accounting authorities to identify the remains associated with the crew and move the case to an accounted-for outcome. This is the decisive technical pivot. The operation did not end in ambiguity or partial recovery. It achieved the highest standard of forensic success. The outcome path is locked. The mystery of the missing aircraft has been resolved into a verified historical fact. The final step is not scientific but ceremonial. The team must now execute the return of the crew to the custody of their nation. The conclusion of the investigation requires one final operational decision regarding the disposition of the recovered elements. This decision is not made by the recovery team or the anthropologists, but by the families of the lost airmen in consultation with the Armed Forces Medical Examiner. The choice lies between individual interment for those members whose remains could be separated and a group burial for the commingled evidence that cannot be biologically divided. This trade-off is the final constraint imposed by the high-speed impact event of 1943. The violence of the crash ensures that while identification is absolute, the physical separation of every individual is not always possible. In the case of B-24D serial number 4240972, the disposition reflected both individually identified remains and group remains representing the full crew. consistent with the commingling realities of high-energy impact. This selection process converts the scientific success of the DNA lab into a formal legal status. The evidence is no longer classified as forensic material. It is reclassified as human remains, and the strict protocols of evidence handling give way to the protocols of military honors. This transition is governed by the chain of custody. Throughout the excavation on the scree slope and the analysis in Hawaii, the chain of custody served as a forensic tool to ensure the integrity of the data. It required signatures, logs, and secure storage to prevent contamination. Now, the chain of custody serves a different purpose. It ensures the dignified transfer of the crew from the control of the laboratory to the control of the cemetery. The documents that accompany the caskets are not just shipping manifests. They are the legal certification that the United States government has fulfilled its obligation to account for its personnel. On February 10, 2006, the case reached its identification milestone. The public announcement followed in July, and on July 19th, individually identified remains of several crew members were buried at Arlington National Cemetery. Along with group remains representing all 9 crewmen, the remaining crew members were buried elsewhere. This specific section is active and serves as the resting place for casualties from recent conflicts, as well as those recovered from historical losses. The presence of the World War II crew in an active section underscores the continuity of the recovery mission. It demonstrates that the timeline of a loss does not expire until the accounting is complete. The legacy of the recovery extends beyond the cemetery gates. Back in the Sarawagid Range, the physical wreckage of the Liberator remains on the mountain. The recovery team removed the human evidence and the personal effects necessary for identification, but the heavy structure of the aircraft was left in situ. Much of the remaining wreckage was left in place on the mountain after the recovery of human evidence and key personal effects. The site is no longer a missing person case file. It is now a verified war grave and a historical landmark. The investigation answered the central question of the disappearance. It proved that the loss was caused by a collision with terrain following a loss of navigational orientation. It proved that the crash was instantaneous and unsurvivable. Most importantly, it bridged the 60-year gap between the stopped clock in the cockpit and the families waiting for answers. The avalanche seal has been broken, the evidence has been extracted, and the crew has been returned. The file on Aircraft 4-240972 is now closed. The mountain keeps the machine, but the men are home.